Good afternoon. Today I will discuss some question based on principle of mathematical induction. Here I have taken one question. Prove by using principle of mathematical induction that the product of n terms of this series equal to n plus 1 whole square. I have denoted that first term by a1, second term by a2, third term by a3 and nth term by an, and product of n terms is equal to n plus 1 whole square. In bracket you see, let Pn denote the product of n terms. Then Pk plus 1 is the product of k plus 1 terms. Thus Pk plus 1 can be written as product of k terms multiplied by k plus 1th term. That is the case. So now we can write, let your P of n is product of n terms like 1 plus 3 upon 1 multiplied by 1 plus 5 upon 4 multiplied by 1 plus 7 upon 9 and so on multiplied by 1 plus 2n plus 1 upon n square, that is equal to n plus 1 whole square. This is 1. Let n equals to 1. Your P1 is the value of first term 1 plus 3 upon 1, and when you substitute on the right hand side n equals to 1 in this, so you will get 1 plus 1 whole square. So your P1 can be written as, this is 4 equal to 2 square is 4. Therefore P of n is true for n equals to 1. Now we suppose that P of n is true for n equals to k. You can write your P of k as 1 plus 3 upon 1 multiplied by 1 plus 5 upon 4 multiplied by 1 plus 7 upon 9 multiplied by 1 plus 2n plus 2k plus 1 2k plus 1 by k square is equal to k plus 1 whole square. This is 2. We will prove that Pn is true for n equals to k plus 1. So in this way, if you can write pk plus 1 equal to pk into ak plus 1. How can you find ak plus 1? So now your an is, you see, your an is 1 plus 2n plus 1, 2n plus 1 by n square. This implies that ak plus 1 equal to 1 plus 2k plus 3 upon k plus 1 whole square. So now you substitute both. Your value of pk is k plus 1 whole square into ak plus 1 is this much, 1 plus 2k plus 3 upon k plus 1 whole square. This thing. Now you solve this. This is equal to k plus 1 whole square into k square plus 2k plus 1 plus 2k plus 3 upon k plus 1 whole square. So this is cancelled. So this is equal to k square plus 4k plus 4, that is equal to k plus 2 whole square. So when you substitute n equals to k plus 1, when we substitute n equals to k plus 1 in 1, we get n plus 1 whole square equal to k plus 1 whole square, that is equals to k plus 2 whole square. This shows that your Pn is true for n equals to k plus 1, hence Pn is true for all n belongs to n. So in this way we will prove this question, the product of the n terms of the given series is true, and it is done by the principle of mathematical induction. Now next question. Now, question number 7. Prove that 1 plus 1 upon 1 plus 2 plus 1 upon 1 plus 2 plus 3 plus and so on plus 1 upon 1 plus 2 plus 3 plus and so on plus n equal to 2n upon n plus 1 for each n belongs to n. So by using principle of mathematical induction, we will prove this sum of the series is true. Now solution, given that, or you say let Pn equals to 1 plus 1 upon 1 plus 2 plus 1 upon 1 plus 2 plus 3 plus and so on plus 1 upon 1 plus 2 plus 3 plus and so on plus n equal to 2n upon n plus 1, this is 1. Now, this is sum of n terms of this series. Now, in this question, there is no product of n terms. Here, you are given sum of n terms of the series. You have to prove that this is true for all natural numbers. Let n equals to 1. So, your P1 is the value of first term, it is 1. That is equals to, when you substitute n equals to 1 on the right hand side in sum, so it is 2 into 1 upon 1 plus 1. This implies that P1 equals to 1 equals to 1. So therefore P of n is true for n equals to 1. Now we suppose that P of n is true for n equals to k. So you can write P of k is equals to 1 plus 1 upon 1 plus 2 plus 1 upon 1 plus 2 plus 3 plus and so on plus 1 upon 1 plus 2 plus 3 plus and so on plus k that is equal to 2k upon k plus 1. This is 2. Now your an is 1 upon 1 plus 2 plus 3 plus and so on plus n. This is sum of n terms of the series. So 1 upon n into n plus 1 by 2. So your an will be 2 upon n into n plus 1. So you can write your an. You remember this thing. From here your an is 2 upon n into n plus 1. So now your ak plus 1 can be written as 2 upon k plus 1 k plus 2. This is 3. This is 2 and this is 3. Now we will prove that Pn is true for n equals to k plus 1. So you can write P of k plus 1 equals to P of k plus ak plus 1. This is 4. From 2 and 3 we substitute the value of from 2 and 3 we substitute Pk equal to 2k upon k plus 1 and ak plus 1 equal to 2 upon k plus 1 k plus 2 k plus 2 in 4 k plus 1 k plus 2 in 4. In 4 we get Pk plus 1 equal to 2k upon k plus 1 plus 2 upon k plus 1 k plus 2. So this can be written as 2 upon k plus 1 is common in bracket k plus 1 upon k plus 2. So you can write 2 upon k plus 1 into k square plus 2k plus 1 upon k plus 2. So you can write 2 upon k plus 1 into k plus 1 whole square upon k plus 2. that is equal to 2 into k plus 1 upon k plus 2, which is true, which is true for n equals to k plus 1, hence P of n is true for each n belongs to n. Now, next question. Prove that prove that 1 into 2 into 3 plus 2 into 3 into 4 plus 3 into 4 into 5 plus and so on plus n into n plus 1 into n plus 2 equal to n plus 1, n plus 2, n plus 3 upon 4 for each n belongs to n. This is the question. Now, solution. Let P of n equals to 1 into 2 into 3 plus 2 into 3 into 4 plus 3 into 4 into 5 plus and so on plus n into n plus 1 n plus 2, that is equals to n plus 1 n plus 2 n plus 3 upon 4. This is 1. Here an is n into n plus 1 n plus 2. So your ak plus 1 is k plus 1 k plus 2 and k plus 3. And now let n equals to 1. So your P1 is the value of first term, it is 6. Now you substitute n equals to 1 in the sum, you will find 1 into 2 into 3 into 4 by 4. So your P of 1 equal to 6 equal to 24 by 4. So P of 1 equal to 6 equal to 6. Therefore, P of n is true for n equals to 1. Now we suppose that Pn is true Pn is true for n equals to k. So you can write your pk as 1 into 2 into 3, 2 into 3 into 4, 3 into 4 into 5, plus and so on, plus k into k plus 1 into k plus 2 equal to k, k plus 1, k plus 2, k plus 3 by 4. This is 3. We will prove that P of n is true for n equals to k plus 1. So we can write again pk plus 1 is equal to p of k plus ak plus 1. This is 4. From 2 and 3, we substitute pk equal to k, k plus 1, k plus 2, k plus 3 by 4, and ak equal to k plus 1, k plus 2, k plus 3 in 4. We get it. So now P of k plus 1 equal to pk. Pk is k, k plus 1, k plus 2, k plus 3 upon 4 plus ak plus 1 is k plus 1, k plus 2, k plus 3. This thing. Now, by taking common, we can write this is equal to k plus 1, k plus 2, k plus 3 in bracket k by 4 plus 1. This is equal to k plus 1, k plus 2, k plus 3 into k plus 4 by 4, which is true for n equals to k plus 1. Hence, Pn is true for each n belongs to n. Now, next question. Question number 9. Question number 9. Prove that 1 upon 2 into 5 plus 1 upon 5 into 8 plus 1 upon 8 into 11 plus and so on plus 1 upon 3n minus 1, 3n plus 2 that is equal to n upon 6n plus 4 for each n belongs to n. We have to prove this result. Now you see, solution. Let P of n equals to 1 upon 2 into 5 plus 1 upon 5 into 8 plus 1 upon 8 into 11 plus and so on, plus 1 upon 3n minus 1, 3n plus 2 equal to n upon 6n plus 4. This is 1. Your an is 1 upon 3n minus 1, 3n plus 2. So your ak plus 1 equal to 1 upon 3k plus 2, 3k plus 5. This is 2. Let n equals to 1. P of 1 is the value of first term 1 upon 10, that is equals to, put n equals to 1 here, so it is 1 upon 6 into 1 plus 4. So P of 1 is 1 upon 10 equal to 1 upon 10. Therefore Pn is true for n equals to 1. Pn is true for n equals to 1. Now we suppose that Pn is true for n equals to k. Your Pk can be written as 1 upon 2 into 5 plus 1 upon 5 into 8 plus 1 upon 8 into 11 plus and so on, plus 1 upon 3k minus 1 into 3k plus 2, that is equal to k upon 6k plus 4. This is 3. We will prove that Pn is true for n equals to k plus 1. So Pk plus 1 is equal to P of k plus ak plus 1. This is 4. Substituting Pk equal to k upon 6 plus k plus 4 and ak plus 1 equal to 1 upon 3k plus 2 into 3k plus 5 in 4. We get that is P of k plus 1 equal to Pk, k upon 6k plus 4 plus ak plus 1, 1 upon 3k plus 2 into 3k plus 5. Now taking common 1 upon 3k plus 2. Here in bracket k upon 3 plus 1 upon 3k plus 5. So you can write that is equal to 1 upon 3k plus 2. Your LCM is 3 into 3k plus 5. Here 3k square plus 5k plus 3. that is equal to 3k plus 5. So in this way you can write k plus 1. Three 3 are 9 by splitting middle terms. Here this is wrong. This is k by 2. Your LCM is 2 into 3k plus 5. This is 3k square plus 5k plus 2. Now you factorize. So this is equal to 1 upon 3k plus 2 in bracket 3k square plus 5k plus 2 equal to 3k square plus 3k plus 2k plus 2. 3k in the bracket k plus 1 plus 2 in the bracket k plus 1. So your factor is k plus 1 3k plus 2. So in this place you can write its factor which is here. So you can write k plus 1 3k plus 2 upon 2 into 3k plus 5. So your this 3k plus 2 and this 3k plus 2 will be cancelled. So it is k plus 1 upon 2 into 3k plus 5. So I hope which is true for n equals to k plus 1, for n equals to k plus 1, hence Pn is true for n equals to k, true for each n belongs to n. Now next question number 10. Prove that question number 10. Prove that 1 upon 1 into 2 into 3 plus 1 upon 2 into 3 into 4 plus 1 upon 3 into 4 into 5 plus and so on plus 1 upon n into n plus 1 n plus 2, that is equal to n into n plus 3 n into n plus 3 upon 4 n plus 1 n plus 2 for each n belongs to n. You have to prove this result by using principle of mathematical induction that this is true. You have to prove this result by using principle of mathematical induction that this is true for all natural number. So now solution. Let P of n equals to 1 into 2 into 3 plus 1 upon 2 into 3 into 4 plus 1 upon 3 into 4 into 5 plus 1 upon n into n plus 1 n plus 2, that is equal to n into n plus 3 upon 4 n plus 1 n plus 2. This is 1. Your an equal to 1 upon n into n plus 1 n plus 2. So your ak plus 1 equal to 1 upon k plus 1 k plus 2 k plus 3. This is 2. Let n equals to 1. So your P1 equals to 1 upon 1 into 2 into 3, that is equals to, put n equals to 1 in this sum, 1 into 4 upon 4 into 2 into 3. So 4 and 4 will be cancelled. So P1 implies that 1 upon 6 equal to 1 upon 6. Therefore, Pn is true for n equals to 1. Now we suppose that P of n is true for n equals to k. Now Pk can be written as 1 upon 1 into 2 into 3 plus 1 upon 3 into 4 plus 1 upon 3 into 4 into 5 plus and so on, plus 1 upon k plus 1 k plus 2 equal to k plus 3 upon 4 k plus 2 k plus 3 upon 4 k plus 1 and k plus 2. This is 3. We will prove that P of n is true for n equals to k plus 1. So we can write P of k plus 1 equal to P of k plus ak plus 1. This is 4. Substituting P of k equals to k plus 3 upon 4 k plus 1 k plus 2 and ak plus 1 equal to 1 upon k plus 1 k plus 2 k plus 3 in 4 we get pk plus 1 equal to, here your 4 is this, your p of k plus 1 equal to p of k plus 3 upon 4 k plus 1 k plus 2 plus ak plus 1 is 1 upon k plus 1 k plus 2 into k plus 3. Now solve this. By solving, you will get 1 upon k plus 1 k plus 2 common in bracket k square plus 3k by 4 plus 1 upon k plus 3. So it is 1 upon k plus 1, k plus 2, here k square plus 3k into k plus 3 plus 4 upon 4 k plus 3. So now this is equal to 1 upon k plus 1 k plus 2 into k cube plus 3k square plus 3k square 6k square plus 9k plus 4 upon 4 into k plus 3. So in this way you can write this is equal to p of k or f of k upon 4 k plus 1 k plus 2 k plus 3. This is 5, where f of k equal to k cube plus 6k square plus 9k plus 4. F of minus 1 is equal to minus 1 plus 6 minus 9 plus 4, that is equal to 0, implies that k plus 1 is a factor of fk. So you find other factors. Now divide k cube plus 6k square plus 9k plus 4 divided by k plus 1. You will get k square plus k square k cube 5k square plus 9k plus 5k plus 5k 5k square minus 4k plus 4, this is 4, so 4k plus 4, your remainder is 0. So you can write, now you can write the factor of k square plus 5k plus 4 is equal to k square plus 4k plus k plus 4 k plus 4. So your factors are k plus 1 into k plus 4. So fk can be written as k plus 1 into k plus 1 into k plus 4. So substituting in 5. Substituting in 5 we get pk plus 1 is equal to k plus 1 k plus 1 k plus 4 upon 4 k plus 1 k plus 2 into k plus 3. So 1 k plus 1 will be cancelled. So you can write this is equal to your p of k plus 1 can be written as k plus 1 k plus 4 upon 4 k plus 2 k plus 3. This is true. to k plus 1. Hence, P of n is true for each n belongs to n. इसमें एक ये देखिए चालू हो गया।